Yes, so the point of this lab, for me, what I want to get you doing is going onto the real quantum devices that are being offered as prototypes and to use them to do actual useful and interesting stuff. And the most useful and interesting thing you can do with the devices at the moment is to do science. Because if you want to do an application, then you have to contend with, firstly, the size of the device, but also noise. Noise in this context is a bad thing. The errors get in your way. They cause you not to have exactly the kind of output you want. But for quantum error correction, noise is what it's all about. And if there was no noise, there would be no quantum error correction. So yeah, noise is something that is a good thing, essentially, for quantum error correction. And so we can study that noise. We can try and work out how it transforms our circuit, how it appears, where it comes from, what kind of effects it has. And I think one of the best ways of doing that is using quantum error correction, because it's a technique that is designed to interact with noise. Also, if you think of the era of fault tolerant, which is something that we are working towards, they will use quantum error correction. And in fact, if you look at what they do on the level of the device, pretty much every operation that is being applied is an operation dedicated to doing quantum error correction. An application is effectively a side gig that a fault-tolerant quantum computer does as well as its real job, which is doing quantum error correction. So if we want to know how well a fault-tolerant quantum computer can work, if we want to know that our hardware that we're building now is compatible with that goal of building a fault-tolerant quantum computer, then we should see how well it does error correction. So you've already learned in the lecture, about quantum error correction. You've learned about the repetition code, and you've learned about the surface code. And so you can start thinking of ideas of how to implement those, and what kind of tests you might want to run, and what you might want to find out about when you run it, and see how it actually interacts with real noise in the wild. One thing you'll find is that the smallest surface code needs 17 qubits, and we have more than 17 qubits on some of our devices, unfortunately not the publicly accessible ones. But even so, they're not laid out in the right way for doing a surface code. In terms of applications, if we want to do CNOTs that the device can't directly do, we know ways of taking gates we have and combining them to make other gates that we need. But it means taking many gates and combining them. And when you do that, you also take their noise and combine them and make huge noise monsters that you don't want to put anywhere near your error correcting codes. So even though we have enough qubits, we don't have the connectivity to run surface codes. But we can run repetition codes on all of our devices, including the publicly accessible ones. And I even have a paper, or papers actually, running repetition codes on publicly accessible devices. So this is something that you can also do, something you can try. It's something you can use to try and understand the devices, and perhaps even understand some of these noise processes more than the people who actually built the devices, and do actual real science. Even if you're not academics, you can do real science using your knowledge of quantum error correction and the devices that we have. But there is something missing in your knowledge in order to be able to do this effectively. And that missing thing is what we're going to look at in the lab, which is some of the tools that Qiskit has, and some of the problems that you will have to solve in order to do experiments like this. And the problem that you'll have to solve is the one that we'll use as the grading in the end. Okay, so often when we begin looking at anything that we're doing with quantum computing, we don't start by running it on a real device. We start by simulating it. But as I said, noise is key to quantum error correction. So the fact that simulations usually don't have any noise is kind of a problem in that regard, because we're not going to get the effects that we need to get. So one thing that we can do in this case is then simulate noise. We can simulate them being bad, even though we can also simulate them being perfect. And Qiskit has plenty of stuff in order to help you with that, and you'll find lots of resources online to tell you about the noise models. So this is not a lecture on noise models, but they exist and you can use them. So I'm going to import noise model, which is the object we use in Python to hold noise models, and a couple of different kinds of, well, a few different kinds of error. Pauli errors, depolarizing errors, thermal relaxation errors are all kinds of typical ones. Pauli errors are where you probabilistically do an X, Y, or Z. Depolarizing error is, actually it can be described in terms of Pauli errors, but it's a more general, well, it's depolarizing errors. It's a fancy thing. And thermal relaxation errors are an even fancier thing. They model thermal effects that, well, relax. So the zero on the one state in an actual real superconducting qubit device, the one state has more energy than the zero state. And so there can be processes that cause that one to decay down to zero. And this is the way that we model those kinds of errors. And I'm just going to make a simple function. If you don't want to think too much about it, you don't have to. And this function is going to make a noise model. So basically, I'm going to have a noise model which has two types of error. It applies depolarizing errors to any controlled knots that it finds in the circuit. And also when you measure, you'll have a thermal error. So the measurement will have this process which causes some decays of ones to zeros. And these are parameterized by probability. So there's some probability which acts as the probability that these errors will occur on the controlled knots. But the thermal errors are parameterized by a set of 3 times. So T1 and T2 are time scales for this thermal process, and we don't really have to go into the details of these. The final time, Tm, is the amount of time it takes to make a measurement. So if T1 and T2 are infinity, then that means that the time scale of relaxation is infinity, and it doesn't matter how long it takes to make a measurement, you will never see this process happen. But if they are not infinity, if they are something finite, like for example 1, then if you take a finite amount of time, then you will see this process happen. So if you take a time of 1, you'll probably see it happen quite a lot. But if you see a time of 0, if you take a time of 0, then you're so quick that you won't see this noise. So these are just default values. The default value here is that you don't have any probability of error on a C0. And the default values here are T1 and T2 just being 1. And then what matters is the ratio between T1 and T2 and the time taken for measurement. So you don't have to worry too much about units. And here I've got the measurements are infinitely fast. So this default value is also going to give us no errors here. Okay, so this is some syntax which makes noise models. I won't go into it in too much detail. Let's look at it in action. Actually, of course, I have to execute that cell, otherwise it doesn't exist. And let's do a quick circuit. This is a circuit in which we do an X on 1 qubit, a controlled knot between another 2 qubits, and nothing on this qubit. So what is the outcome of this? Well, what does the X do? It flips a 0 to a 1. What does this controlled knot do? Well, it does nothing. You probably, you might notice that because it's acting on a control qubit, which is in state 0, it's not going to do anything. So in terms of actually a circuit, it's pretty useless, but we're using it to look into the noise. So let's now run it. If we run it without noise, then we see a 1 on the qubit that the X acted on, and a 0 for the 2 qubits that the control knot acted on, and then another 0. So now let's run it with noise, but we'll just turn the noise on for the controlled knot gates. And what we find here is that we get various different results. So this runs it 8,192 times, which is a nice round number. And in each case, we still get this 1 here from the X. So I don't need to highlight them all, but it looks like I will. And on the other side, for the qubit that has nothing happen to it, we always get a 0. It stays in its 0 state. But the other 2 qubits, the ones on which a controlled knot act, they're no longer in their 0, 0 that they should be, but they're equally likely to be 1, 1, 0, 1, 0, 0, or 1, 0. I got those two mixed up. You know. So they have just had complete noise. So it's not actually a controlled not happening there. It's just random nonsense. So here you see some noise. If we had this noise being more reasonable strength, we would see that the right answer is very much the most likely answer. The idea of them getting both flipped is the less likely answer. So now let's do it for a range of measurement times, and we find that the shorter the time, the more it comes out the answer it's supposed to be. So this is very heavily biased towards the right answer, and there's a few cases where this 1 instead gets flipped to 0. So this measurement error is occurring on all the qubits. And no, I think I'll put the blind down. The sun seems to be coming in. So the measurement error occurs on all of the qubits, but it's only that last qubit, the one with the 1, or the first qubit, that is getting affected. And the reason why is that the way that we define this is that it's going to cause relaxation errors, 1s to turn into 0s. It doesn't really cause 0s to turn into 1s. So this is the only one, so this is the only one getting affected. There's a few cases in which this 1 goes down to a 0, but if we up the amount of time we take for the measurement to much longer than the time scale of the relaxation, then we find basically that they have all decayed. So it's a random process of decay, but if you run it long enough, you get to this fixed point. Okay. Now, that is noise, and so that's something that we might want to have as a tool in our pocket when we are looking at error correction experiments, because we might want to simulate noise and compare how our simulations of noise compare to real noise on devices. Now we want to run repetition codes. So as I said, repetition codes are codes that can run on current devices, and as such, we have tools in Qiskit to help you do that. We have this repetition code class, which creates repetition code. We have graph decoder, which does the decoding. And we have these other decoding methods, which are not so scalable, but they do have their uses. And in fact, in my first paper doing a repetition code, it's lookup table decoding that I used. So let's import those things. We just need to decide how many code qubits we have, so how many times we're actually going to repeat the message, and how many measurement rounds we're going to do. And with current devices, we can't measure the same qubit more than once. So the fact that we can only measure the same qubit once means that we can only measure our ancilla qubits one time, so we can only do one round, one repetition of the process. So let's set up a repetition code object that is has 4 repetitions and 1 round. And this has an attribute circuit, which has a couple of circuits in. One of these circuits is for if we're encoding a 0, so we're repeating the 0, and the other one is for when we're encoding a 1. So here is the circuit for 0. You'll notice it's in the beautiful text-based form. That's because these underscores really don't agree with the fancier one. But it's always nice to be a bit retro, isn't it? So here we have our code qubits, and we have our ancillas, and you can see, for example, this ancilla is has 2 controlled knots on it, controlled by 2 different code qubits, code qubit 0, code qubit 1, so it's measuring parity over those 2. In exactly the way that we described in the lecture. And then we have various bits where we're taking them out. So there's all kinds of technicalities that you don't have to cover in our lecture. The only difference with the circuit for 1 is that we have these X gates which flip all of the code qubits to 1, so that we're repeating 1s across the code qubits rather than 0s. So let's now run them. So if we want to run them, we can use execute, and execute takes either a circuit, a single circuit, or a list of circuits. But what we are getting out of this object is a dictionary of circuits. So, okay, this is just Pythonic technicalities, but we have to convert that list into a dictionary in order to run it. So But the code object does just have a method get circuit list, which does that for you. So we'll turn it into a list called circuits, and then we run them, and then we see what happens. Oh, actually, we've got to extract the results because this is a job object. And also the code object has this method process results, which makes the results look more sensible from the format of quantum error correction. So let's do that. And actually, instead of doing all of this every time, we could just make a function which would extract the list, run it, extract the results. So let's do that in the future. So if we were to do that with an empty noise model, we would get a result that looks something like this. And what we're seeing here is these results are the results of the three ancilla qubits. So they're telling us these parities. We've got 4 qubits, and so we've got 3 measurements where we compare the parity of the first and the second, and then the second and the third, and then the third and the fourth. And we want those all to come out 0, telling us that we've got even parity and everything's okay. And this is exactly what's happening here. Then at the end, we measure all of the code qubits. So that's 4 measurements. But when we measure the code qubits, we can also extract that parity information. We can manually look at the first and second qubits and say, are they the same or different? And then write that parity out. And then we can manually look at the next 2 and see if they're the same or different and manually write that out. So that's what is done here. That's what this second block of 3 means. It's also parities, but these aren't directly done by the ancillas, but they are extracted from the final readout. And then these 2 are just telling us what the logical value is on each of the ends. So when we measure the code qubits, it's telling us what the first code qubit was and the last code qubit was. And the reason why it does that on 2 of them and not on all of them or 1 of them or any other combination is because it has nice properties for the graph decoder, which you can find out about in some of the further reading. So you find out, so yeah, for these cases where there is no noise, then all of these parity measurements come out as being everything's good because there's no noise to make it bad in both the case of encoding a 0 and encoding a 1. And these ones that reflect the logical readout are 0s when we're encoding a 0 and 1s when we're encoding a 1. But if we were to put some noise in there, we would find that things change a bit. So we would find that, so these are just some of the most common results for a noise model with, I just put some controlled not noise in at a particular strength. And you find that the most likely result is the right one, but you also see here is a case where an error flipped one of the qubits and therefore caused 2 of these parity checks to report that something had gone wrong, but it didn't do anything other than that. Sometimes it causes 1 parity check to flip because it's on the end, but it also causes the logical value to flip. So they always occur in pairs, which is nice. And in fact, that's why we choose to take the edges. But yeah, you can read about that more in some of the further reading. So from the results, something that we need to know the most is the probability of a logical error. So what is a logical error? It means if you gave someone this as a result and they knew exactly what format this was in, and you said, okay, this is the result that I got from my quantum computer after I encoded a bit value and stored it for a while using a repetition code. What value did I store? Can you guess? Then someone has to do this process of trying to work out from this result what you encoded. And they'll probably see, well, one of these parity checks is reporting something went wrong over on this end, and this value corresponding to the same end, I'll probably then not trust that as much. But over this end, everything seems fine, so let's trust this value. I think you encoded a 0. Yeah, you're right. But what is the probability that you're wrong? Because this is not just a game that you play with your friends, it is what we need to do in order to do fault-tolerant quantum error correction. So We can create then a decoder object using Qiskit, which will just do the decoding for us, will solve this problem for us. And then we can run this get logical prob method in order to solve this. And we find in this case, the probability of getting it wrong is very, very small, on the order of 0.02, whether we're encoding a 0 or a 1. And this is less than the noise. So it is less likely than the noise, which is good. It shows that things are going well in the world, which is what we like. And if we had the noise lower, then we would find that our error correction process is even better. Now we've got even more zeros. So by decreasing the error or by increasing the number of qubits, we should get better error correction. So by calculating these values for different sizes of code and different noise model, then we can get, and for different qubits on a device, we can learn how the noise is going to affect that process. We can learn about the noise. Now, what is that qubit doing? Why is that qubit doing something a little bit weird? Why, when I add this qubit, does everything go a little bit strange? You get insights into devices. You can then compare these with the noise models that we extract from them. You can see if they're covered in the noise model, or is there some other kind of noise that doesn't seem to be covered there? Is there some sort of a mystery that needs to be solved? Now, this is something that I found when running repetition codes for papers that I've written. I found results that don't seem to make sense. They're the exact opposite of what I would want. And then I can look into that mystery and try and solve it. And I get some insight about what's actually going on. And I see the physics of the noise, which is something that we can really study at this time. It's a very interesting thing that we can do at this point in quantum computing. So if you want to see some more examples of that, then you can check out the papers I have. So I've got one from a couple of years ago, and I've got one from just this year. And there's also the relevant chapter, of course, of the Qiskit textbook that you can look into to see how you do this. But there is one puzzle you always have to solve when you are running on real devices. And this is that you have to really know your device. You have to know where its qubits are, which qubits talk to which other qubits, and plan for that. So that means you have to not just let the transpiler do things on its own, but you have to think about the process of transpilation. For that, we need to load our IBM Q account, and we need to get our provider. And let's have a look at the biggest device that is publicly available, which is IBM Q16 Melbourne. So we set up the backend object in this way. And so I'm often glossing over the code a bit because this is not sort of a lecture in Python, and you can pause and you can go back so you can look at these things in more detail, and you'll have the notebook to look into explicitly. And of course, you can always Google the syntax. Do provider.get backend, Control-C, go and Google that with Qiskit, and it'll tell you all about that. Well, hopefully. Anyway. So we've got these called Jupyter tools, which give us nice insight into devices. Once it runs, it will show us something pretty. So you can see everything about the device. For example, that it's not on today. But I'm not going to run anything on it, so that's not a big problem. So this is its coupling map. This is a qubit. It's called 0. This is another qubit. It's called 1. And this is a qubit called 14. And 0 is only friends with 1 and 14. It is only possible to do controlled knots between 0 and 1 or 0 and 14. It's not possible to do a controlled knot directly between 0 and 13. You have to come up with some of these transpilation tricks if you want to do something like that. And so if you ever run a circuit which has a single qubit that is involved in controlled knots with more than 3 other qubits, and you run it on Melbourne, then those controlled knots in your circuit do not directly correspond to the controlled knots being applied on the device, because there's just not the possibility. There is no qubit on here that can talk to 4 others, as an example. So, and this is an example that's pertinent, of course, for the surface code. So there would have to be a transpilation process there, which would, for example, if you wanted qubit 1 to talk to 4 others, maybe you'll make it talk to 0, 2, and 3, but also 14. And then when you make it do it with 14, you do a swap gate on 0 and 14 to move the state of 14 over here, and you can do a controlled NOT, and then you do another swap to move it back. But that swap is a non-local process, which is also making the noise non-local. Something that was a single qubit error, when you do a swap, becomes a multi-qubit monstrosity. So this is why it's hard to do quantum error correction experiments, even if you have enough qubits. Yeah, so this is the coupling map we have, but one thing we can do is we can do repetition codes, because repetition codes mean we have to have a code qubit talking to an ancilla qubit, which talks to another code qubit, which talks to another ancilla qubit, which talks to another code qubit, which talks to another ancilla qubit, and so on and so forth. It only needs a 1D connectivity. So we just have to find a line that stretches across the device, and then we can do it. And the only thing that makes that problematic is this 7 being on its own. So if you wanted to go, if you just went 0, 1, 2, 3, 4, 5, 6, 8, 7, oh, you've painted yourself in a corner, so you have to make sure you don't do that. So it's a puzzle to solve. And obviously it's an easy puzzle, but it's a puzzle. So let's do some transpilation. Sorry. So d equals 8 is the largest code that we can do on here, because that means we have 8 code qubits and 1 less than 8, which is 7 ancilla qubits, so that's 15, and the number of qubits on this device is 15. So, well, that's a simple proof, isn't it? So let's do a d equals 8. So we've created now a d equals 8 code object. We have taken the circuits and made them into a list, and I've called these raw circuits because they're not the circuits that the device is actually going to run. For that, we first have to transpile. So let's look at that transpilation procedure. First, let's have a look at the circuit. Now, if I did the circuit diagram, it would be huge, so let's not do that. Instead, we could just look at what gates it has. So if we look at the circuit encoding a logical 1, it has 8 X's required to flip the 8 code qubits to their 1 state. It has 14 controlled NOTs because there are 7 ancillas, and each of them has 2 controlled NOTs in the stabilizer measurement that it is involved in, so that makes 14. And we have 15 measurements because we measure all the qubits and there are 15 of them. Okay, now let's transpile it. So we're going to make a new list called circuits, and circuits means we're going to go through the circuits in raw circuits. We are going to transpile them, and we're going to put them into this new list. So the circuit at circuit 0 is going to be the transpiled version of raw circuit 0. And circuits 1 is going to be the transpiled version of raw circuits 1. And to transpile, we just say transpile, and we have the circuit we want to transpile, and we have the back end that we are transpiling it to. So it's a device that we are making the circuit on which it can run, because it differs from device to device because the coupling map differs from device to device. Okay, I haven't run that yet, have I? So let's run it. And so this is what raw circuits 1 was, the circuit for logical 1. And now let's see what the transpiled version is. Okay, let's put a barrier in there. Fair enough. That's mostly that's not really a physical operation, so I don't care. And what has it done to our X's? We had 8 X's, and now we have no X's. Well, actually we do. So from a physical so X is kind of like an abstract concept of a gate. In terms of the physics of the gates, it usually describes things in terms of U1 and U2 and U3 operations, which are just single qubit operations parameterized by numbers. And that is the language a device speaks. So instead of calling it an X, we have to call it a U3 with 3 given numbers, which corresponds to an X. So that is just our X's. We still have 15 measurements. And what about our 15 controlled NOTs? Well, we have at least 15 controlled NOTs. So That's something. So why do we have 71 controlled knots? Well, earlier I told you that if we try and remap, so if we try and move the qubits, the states of the qubits around, we use swaps. So in order to take a circuit which can't directly be run on the device and make it so it can be directly run on the device, we use tricks like swaps. And swap gates are not something that the device can run naturally. It has to be expressed in terms of the gates that can be run on the device naturally. One of those is the controlled knot. So with 3 controlled knots, you can make a swap. So to swap and then swap back, that costs 6 controlled knots. So it's fairly expensive in terms of the controlled knot cost. So what we're seeing here in the increase in the number of controlled knots is that the transpiler has used some of those tricks to make it so that the circuit can run on the device. And this may be because when we give it the circuit, it maybe thinks of the first code qubit as 0, and then the second code qubit as 1, and the third code qubit as 2, and the fourth code qubit as 3, and then once we run out of code qubits, it starts thinking of the next lot of qubits as the ancillas, and it realizes, hang on, I can't entangle 0, the first code qubit, with, I think it's then perhaps 8, the first ancilla. I need to do some transpiling there, and it finds ways to do this. It finds ways to jiggle things around in order to make it work. But the trouble is that it could find a way that didn't require any remapping. It didn't require any controlled knots. But the trouble is, in general, finding out if a circuit can run on a specific device and then making that happen without doing any remapping, without doing any swap gates or other such tricks is a pretty hard problem. So it's not one that the transpiler tries to do with complete accuracy. Instead, it goes the other option of adding in control knots. So if we are very opinionated about the fact that we don't want it to do that, then we have to put in the hard work ourselves. We know it can run on that device because we just looked at it and saw it could. So let's tell the transpiler that information so that it does not have to think. Yeah, so if you want to know more about these ways that we can remap gates, then you can find some of these tricks in more circuit identities. So we do this by in getting the transpiler. So we call it a transpiler rather than a compiler, to be a little bit technical. So a compiler usually takes something abstract, like a programming language, and then expresses it in a more basic form, like in the machine code that actually runs on a computer. But we call it transpilation because we have a circuit which is a perfectly valid circuit, and we turn it into another circuit which is a perfectly valid circuit. So it's not going down in abstraction, it's just being converted into a language which is more suitable for the device that we're using. So that was just an aside, really. What we need to tell the transpiler is which qubits we want to, on the device, we want to play the role of which qubits in our circuit. And this is the way I do it here. So I pick the line that I want to use. So this one that goes from 6 down to 0 and then 14 up to 7. I manually use my hands to write this list 6 down to 0, then 14 up to 7. And then I give this to this function that I've made, which just goes through the qubits in my circuit and then creates this dictionary initial layout, which will pair up the code in my circuit. So this is a particular code in my circuit. And this is so in repetition code objects, you have as a attribute the quantum registers. So that's what I'm using to do this. But in circuits in general, you have as attributes the quantum registers. So you can do this also for circuits. and then I make correspondences between the code in my circuit, so a particular code qubit in this case, and one of these numbers in this line. So if you did this for j equals 0, it would be saying code qubit 0 is the qubit at position 0 in this line, which is this one. And then it would be saying that link qubit 0, the first ancilla, is the qubit at position 2 times 0 plus 1, which is 1, the 1, which is 5 in this line. And then for j equals 2, j equals 1, you get that code qubit 1. So the next code qubit is at position 2 in this line, so 4. And so on and so forth. So remembering that this is indexed from 0, so this is position 0, position 1, position 2, and so on. So you're explicitly saying, I want this particular qubit in my code, in my circuit, sorry, to be this particular qubit on the device. And you build this list of pairs and as a dictionary, and that's something then you can give to the transpiler. So here, this qubit, which is in the quantum register called code qubits and is code qubit 0, is going to be 6. And then the next one along my line, which is 5, is link qubit 0. And the next one along my line, which is 4, is code qubit 1. And the next one along my line, which is 3, is link qubit 1, so on and so forth. With this, we can put that information into the transpilation process, and what we find is that the number of controlled knots is 14. It has used that information to not do any of these transpilation, remapping, swap gate tricks, and actually use the qubits that we wanted to use. So we know when we get results from a particular qubit, we know that that is going to be exactly the qubit that we think it is. Okay, so now a task for you. We used to have a device called Tokyo. It wasn't a publicly accessible device. But one thing that is publicly accessible and still accessible is fake Tokyo. It's like a fake backend that can be used for testing. And in this case, we're testing compilation. So let's use as our backend fake Tokyo. You won't be able to run anything on fake Tokyo because it's fake. But you will be able to use it in terms of compilation because it does have information about Tokyo, including the coupling map, which is this correspondence of which qubits can talk to each other. And that's what the transpilation is based on. So this has 20 qubits, and this is the coupling map. 0 can talk to 1 and 5. 1 can talk to 2 and 7 and 6. 11 can talk to 5, 10, 6, 12, 16, and so on and so forth. This is a coupling map. So this is 4 can talk to 8 and 3 can talk to 9. It's not that 4 can talk to 8 and 3. In fact, 4 cannot talk to 3. So this is, so when I say talk to, I mean you can do a controlled knot, which covers both of those qubits, which is the qubit form of talking. Well, except for when they talk via noise, which is not the kind of talking that we want. So this is what Tokyo looks like, and it has 20 qubits. So what's the largest instance of a repetition code that we can run on Tokyo? Well, we would need, if we had a D equals 10 code, that would need 10 code qubits and 9 ancilla qubits, which is 19, which is less than 20. For 11, we would need 11 code qubits and 10 ancillas, which is 21, which is too much. So a D equals 10 code is the best that we can do, requiring 19 qubits. 19 qubits along a line. Now, how do you do that? Okay, let's just do it. Blah, 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 blah. Okay, I'm lost now. The fact that the coupling map of this is so weird makes it a not entirely trivial problem. It's not too hard. It's a puzzle. It's a nice puzzle that you find in magazines that middle-aged and older people are very fond of. So if you find it hard, give it to your parents, and they can probably do it for you, or anyone else. So also, sometimes when this is run, if you run it in the quantum experience, you'll find this weirdness underneath. Don't worry too much about that. If you run it other places, you might find even more weirdness. It's these fake backends. Well, you know, they're not the things that most people interact with all the time, so they're more likely to have bugs. So let's run a d equals 10 circuit. So we say d equals 10. We set up a repetition code with d equals 10. We extract the circuits. Let's look at the circuit for a logical one. It has 19 measurements. It has 10 X's, and it has 18 controlled knots. That's what it should have. Now let's just take a line. Well, let's say that we want qubit 0 to be our first code qubit, and qubit 1 to be our first ancilla, and qubit 2 to be our next code qubit, and then 3 to be the next ancilla, and 4 to be the next code qubit, and 5 to be the next ancilla. This is obviously not a workable plan. The transpiler is not going to like this because some of those connections are not there. So if we transpile this, we find that, well, the number of control knots it takes is 83. And in fact, you might get different numbers because I think there's a degree of randomness, like 85 this time. The luck was against us. If we run it a few more times, maybe we'll get less. Maybe if we run it enough times, oh no, if you run it enough times, you'll still have the wrong line. So you're still going to be unlucky. But yeah, we see that this is bad. So what we need to do is replace this. We need to replace this with a line, an unbroken line that does not overlap itself, does not cross itself, that goes across the device and covers 19 qubits. You need to find that, and once you find that, you can run a 20 qubit repetition code. Sorry, a 19 qubit repetition code. Well, in theory at least. This is fake. This is a fake backend, so you don't run anything. But if you were to look at the other devices that we have and try and run repetition codes on them, you will have to solve this problem for all of those devices. If you look at devices we will have as we go forward, you will have to solve this problem in order to run repetition codes. So this is the task that I'm giving you to solve this transpilation problem for this specific instance. And also, you might want to try different lines across a device in order to get different insights into the noise. So working out how to do this is a good task, so I would suggest you do that. So what you then need to run is, of course, import the grading tools and do this, and you will be submitting your circuits 1 that you've got out of this line, this section here, with your name and your email and so on and so forth. So it should be exactly from here. All you need to change is this line. So actually, I've not given you a lot of Qiskit that you have to do. You have to more think about how your code corresponds to your device. But I have given you a lot of Qiskit that you can use to use this knowledge of quantum error correction that you have learned to do actual science. And I hope, more than solving this puzzle, I hope that is what you do as a result of this lab. So that is all. I wish you a good weekend, whether you use it doing real science using genuine quantum devices, or, you know, playing Animal Crossing or something. Have a good one.